So let's talk about infinite limits. So when we're talking about infinite limits, we can be talking about something like the following function here. Y is equal to 1 over x squared. Now, when it comes to working with limits, it's always best if we have a visual. If we are able to draw it and graph it out, visually, it really just helps us see what the limit actually is. So if we're looking at graphing this function right over here, so the first thing that I would start with is if you set your denominator equal to 0 and solve, which would give us x squared is equal to 0, take the square root of each side, but x is still 0. That tells us that we have a vertical asymptote at 0 here. Now, horizontal asymptotes, if you compare the degree of your numerator to the degree of the denominator, right? We don't have a variable in our numerator, so that's definitely less than our denominator, which also tells us that we have a horizontal asymptote at 0 here. Now, as far as x and y intercepts, to find your y intercepts, you would plug in 0 into the function. But if we plugged in 0 here, again, we get 0 in the denominator, which is undefined. That means we actually don't have any y-intercepts here. We actually don't have any x-intercepts as well. X-intercepts, you would set your numerator equal to 0 and solve, but that's like setting 1 is equal to 0, which gives us nothing. So there are no x-intercepts. So what I would recommend is just plugging in a point on the left, plugging in a point on the right. So like if I plugged in a positive 1 for x, you get 1 over 1. So we'd get a point right over there. If I plug in negative 1 for x, you would still get a 1. So you get negative 1, 1. So this graph actually, if we take this point and we follow the lines of our asymptotes, so we follow the curves there. Again, keep in mind, your graph wants to be near your asymptotes. So it looks something like this. So we can have a visual so that we can then answer the following questions. The limit as x approaches 0 of 1 over x squared. So notice it's just as x approaches 0. It doesn't say approaching 0 from the left, doesn't say approaching 0 from the right. We are approaching 0, which means that we are coming from both directions. So kind of think about just following your graph, right, from left and the right as we get close to this line here of 0. So the closer and closer we get to that line, our graph is shooting up, 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 right? And it's just going to keep going and it's going to keep following that line. So it's going to keep going up, 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 which gives us a positive infinity for that. The closer it gets to 0, the higher and higher it's going to go. And again, it's going to continue shooting upward towards a positive infinity. If we take a look at the limit as x approaches negative infinity, all right, so we're approaching negative infinity, so we're going this direction. The further we get left, this graph is just going to continue to go, go, go. It's going to continue to get closer and hug the y equals 0, our horizontal asymptote here. So the further it goes left, the closer and closer it's going to get to 0. So the limit here would be 0, which would actually also be the limit of 1 over x squared as x approaches positive infinity. The same would be true there, right? The further we go to positive infinity, again, it's just going to get closer and closer to that line, closer and closer to 0. Okay, so let's take a look at another example here. So let's use the graph to find the following. So we're going to find the limit as x approaches 1 of x over x squared minus 1 squared, right? And then the limit as x approaches negative 1 of that same function. So for this problem, they want us to use the graph to help us find the limits. So that means that we want to be able to graph this thing, all right? So if we're graphing this here, so x and y intercepts, in order to find your x-intercepts, you want to set your numerator equal to 0 and solve. Our numerator is just an x. That would give us x is equal to 0. So that does tell us right here at 0, we have an x-intercept. Now, a y-intercept, you would plug in 0 for x and simplify. We would get a 0 up top. Well, and, you know, we would get a 0 up top if we plug in a 0 here. 0 squared is this 0. 0 minus 1 is a negative 1. And negative 1 squared is a 1. So we're left with 0 over 1 or just a 0, which gives us that same point there. Taking a look at asymptotes. Vertical asymptotes, you want to take your denominator, set that equal to 0 and solve. So we would take that quantity, that x squared minus 1 squared, set that equal to 0. Take the square root of each side to give us x squared minus 1 is equal to 0. Add that 1 to the other side, giving us x squared is equal to 1. Taking the square root of each side gives us that x is equal to plus or minus 1. Those represent our vertical asymptotes. So at a -1 and a +1, we have vertical asymptotes that we can add to our graph. Taking a look at horizontal asymptotes. Horizontal asymptotes, you compare the degree of your numerator to the degree of your denominator. The degree of our numerator is a 1, that is x to the first power. The degree of our denominator is a 4. This is x squared, but keep in mind that that is being squared, so that is actually x squared squared. So do 2 times 2 to get 4. So x to the first over x to the fourth. Numerator is definitely less than the denominator. And if that is so, it means that your horizontal asymptote is at 0. Now, the rest of this, we're just going to be plugging in points, right? Since the only points we got were from our x and our y intercept, we're expected to plug in points on the left, in the middle, and on the right-hand side. Now, just to save us a little bit of time with this example, I'm going to go ahead and plug in here, right? So I would just plug in something to the right of 1, right? Make it a 2, right? And plug in points here accordingly. Your graph is going to look something like this. Here in our middle section, this is going to look like a positive cubic function. So it's going to go up like this and then down like that. In the left-hand section, we have a graph in this bottom left corner that's going to kind of mirror this top right side. That's going to look something like that. You can use a graphing calculator to go ahead and just plug this in and verify and help you get the graph as well, right? The problem does want us to use graphing to help us find the following limits. So whether you graph by hand or you're able to graph with a graphing calculator or a site online, right? Gives us this graph right over here. So we can now answer the questions. The limit as x approaches 1 of this function. So we're approaching a 1, which means, again, it doesn't have a plus or minus here. We're approaching 1. So we're looking at it from both directions, coming from the left side, coming from the right side. The closer and closer that we get to this line, again, we're approaching that line, and it looks like the more we approach the line, our graph is going to just go up, 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 and it's really just going to forever hug that asymptote. This graph is just going to keep going on and on and on from the left and from the right side, and it's never going to stop going. So that means the limit here is going to be a positive infinity since it is shooting upwards forever. The limit as x approaches -1. All right, so we're looking at -1 now from both directions. And if we're looking at -1, the closer and closer we get to this graph, right, we're following the lines of our graph as we get to this barrier here. So as we follow our graph and get closer and closer, notice that our graph is going to shoot downwards. And it's going to keep hugging that line, and it's going to go, 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 and it's never going to stop. And since it's going in the negative direction without stopping, the limit as x approaches -1 of this function would be a negative infinity. So let's talk about this example where g of x is equal to the following, and we're going to find the limit of these 3 things here. So we're going to find the limit as x approaches 1 of this function, as x approaches 3 from the left-hand side, and as x approaches 3. Now, if we're going to find the limit of this, we are going to use graphs to help us find the limit of this function. So that means that we need to get an idea of what this looks like. Now, if you are able to use a graphing calculator, if you have one handy, you can go ahead and plug this in, maybe find a graphing website, plug this into it. If you are a student and you are not allowed to use graphing calculators, it would be in your benefit to learn how to graph this by hand. So if we are talking about how to graph this by hand, so x and y intercepts is what I would start with first. You're going to get your x-intercepts by taking your numerator, setting it equal to 0, and solving. So if I do that, that gives us x minus 2 is equal to 0. Add 2 on each side, and we do have an x-intercept here at a 2. In order to find your y-intercepts, you plug in 0 into the function. So plug in 0 for x. So in the numerator, we would get 0 minus a 2. So that would just be a -2 in the numerator. Right, if we plug in 0 here, that leaves us with negative 1 squared. Negative 1 times negative 1 is a 1. And over here, again, we're plugging a 0, so that gives us a negative 3 there. That really just makes this negative 2 over negative 3, which is a positive 2/3. So that is our y-intercept, a positive 2/3 right over there. The next thing I would find are your asymptotes. Your vertical asymptotes you get by taking your numerator, setting them, taking your denominator. Right, your vertical asymptotes come from taking your denominator, setting it equal to 0, and solving. Now, our denominator is in factored form, which actually works out great for us. Because if it's in factored form, we could use the zero factor property, which says split the factors up, set them each equal to 0, and solve. So I'm just going to add 3 on each side over here, and I get that x is equal to a 3. Right, for this one here, get rid of that square by taking the square root of each side so that we can drop down that x minus 1, and it equals to 0. Add 1 on each side, and x is equal to a 1. This tells me that I have vertical asymptotes at a 1. I also have vertical asymptote at a positive 3. Horizontal asymptotes come from comparing the degree of your numerator to the degree of your denominator. So in our numerator, the degree of our numerator is a 1. If we were to multiply everything out in the denominator, we have an x squared times an x to the first. X squared times x to the first is x cubed. So we have an x to the first in the numerator, x cubed in the denominator. That does mean the degree of the numerator is less than the degree of the denominator. This tells us that the horizontal asymptote is at y is equal to 0. Now, the rest of the graph we can fill in by plugging in points. So on the left-hand side in this section, if you know a little bit about rational functions and the way that those graphs look, given this one point shooting upward, our graph is going to want to hug that asymptote and follow that line. Same thing here on the left. Once you go past this point, it is going to curve here, and it's going to follow that horizontal asymptote. In our middle section, just to help us out a little bit over here, it is going to look like a negative cubic function. It's going to shoot off this direction on the left, this direction on the right-hand side. You can plug in points on either side of it to verify, or again, use a graphing utility. On the right-hand side, we do have a point over here in this space, which is going to mirror this space over here on the left. So it's going to come down just like that, again, following our asymptotes. So now that we have an idea of what this graph looks like, we can answer the following questions. The limit of g of x as x approaches 1. Here is 1, which means as we get closer to this line, again, following our graph, right, moving from right to left, left to right here from both directions, we're going to get closer and closer to that line, following our graph as we get closer and closer. And the closer and closer we get to that line, we see that on each side, it is shooting upwards and it's never going to stop. That means the limit as x approaches 1 is going to be a positive infinity. The limit as x approaches 3 from the negative side. So this is our positive 3. We are coming from the left-hand side. So only from the left-hand side as we get close to this barrier here. Following the left, the closer we get to that line, it's going to shoot down, 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 and it is going to go off to negative infinity for that one. Our last one, limit as x approaches 3. So notice it doesn't have a plus or minus. So we are looking at 3 from both directions. And if we are looking at 3 from both directions, notice on the left, we just answered this, it shoots down to negative infinity. But on the right side, the closer it gets to this line, it's shooting upwards. And because we're going down on one side, up on one side, it's a disconnect. They're not going the same direction. If they're not going the same direction, we say that the limit does not exist for that one. Now, the next couple examples that we're going to look at, we're going to find the limit of the following functions analytically. So we're just going to use rules of functions or rules of limits that we know in order to figure out where these limits are going to. So if we find the limit as x approaches 3 from the right-hand side of this limit. Now, one of the most common ways to find the limit is to take the value that it approaches and to plug it into your function. Now, if I take a 3 and plug this in, and I always start with plugging it in your denominator, because if you get a 0 in your denominator, it's undefined, and we don't want that. And we can see if we plug in a 3 here, we would get 3 minus 3, which is a 0. But let's try something just slightly different here. If I plug in a 3 into my numerator, all right, we get 2 minus 5 times 3. That's 2 minus 15, which is a negative 12. So I would get a negative 12 up top. So the numerator is going negative. Now in the denominator, we already plugged in 3 and we got a 0, but we can use the fact that we are approaching 3 from the right-hand side. So if we're looking at our number line and approaching 3 from the right-hand side, we can actually choose a number that's directly on the right-hand side of 3. Maybe just think like 3.1. Right, since we are coming from this direction, we can grab a number right to the right of 3. So if we do that and we do 3.1 minus a 3, we would be left with a 0.1. Now, 0.1 is a very, very small number, and what we should know about fractions is the smaller your denominator is, the closer it is to 0, the more your function is going to shoot to a large number. So think about it this way. If I have like 10 divided by a 2, we know that that's a 5. 10 divided by 1 is a 10. 10 divided by a half is 20. And the smaller and smaller I make the denominator, notice I started with a 2, then a 1, a 0.5, and I can keep making that denominator go smaller and smaller and smaller. It's going to equal something bigger and bigger and bigger. All right, so the smaller your denominator is, the closer it is to 0, the bigger your overall function is. So we can use the sign of our function along with that fact to say that, well, our numerator is negative, our denominator is positive. Negative divided by a positive is negative. And since our denominator is super, super small, we can say that this then function is going to shoot off to infinity the smaller that denominator gets. So by that, we can say that the limit as x approaches 3 from the right-hand side is negative infinity. Again, because the sign of this function is negative, and because the denominator is so small, the function is going to get larger and larger and larger towards negative infinity. Very similarly over here, the limit as x approaches 3 from the left-hand side of the same function. If we are approaching it from the left-hand side, we want to pick a number on this side super, super close to 3. Let's call that 2.9. All right, so we're going to use that for the denominator. If we plug in 3 into the numerator, again, it is the same numerator. We are getting a negative 12 there. For our denominator, again, we don't want to use 3 because we'll get a 0. So we're going to use a 2.9 since we're coming from the left side. 2.9 minus 3 is a negative 0.1. All right, so let's compare. Our numerator is negative. Our denominator is now negative. Negative divided by negative is positive. Because our denominator, once again, is so small, a small denominator makes your function go large. So this function is going to get larger and larger and larger the smaller the denominator gets, which means it's going to go to infinity. Positive infinity for this one, again, because the sign of our function is positive, and it is going to shoot off to infinity. All right, so let's talk about how do we find the limit as x approaches negative 4 from the positive side of the following function here. So whenever finding limits, again, you always want to try plugging in the number that it approaches. So this one says as x approaches negative 4. So the first thing we would want to try is to take that negative 4, plug it into your function. Now, if we plug in negative 4 into our function here, well, negative 4 times negative 4 times negative 4 is a negative 64. So this would actually be a negative 64, right, which is a positive 64. All right, over here, negative 4 times x squared. Again, we're plugging in a negative 4 here. Negative 4 times negative 4 is a positive 16. And 16 times negative 4, well, is a negative 64. So we would get a 64 minus a 64 here in the denominator, which would give us a 0 in the denominator, which would make this function undefined. We actually would also get a 0 in the numerator, making this 0 over 0 if we were to plug in a negative 4. Now, that is not what we want. That's not what we're looking for here. We don't want to get something in the form 0 over 0. So when this happens, we want to tweak our function here by doing some algebra. Sometimes that's factoring, sometimes that's multiplying by the conjugate, sometimes it's just breaking it down, however which way. It really kind of depends on the function that you are given. Now, I notice that my numerator and my denominator are both polynomial functions, and typically with those, one of the first things you do want to try is to factor the problem. Now, I can see I can do a little bit of factoring here because my leading term is negative, so I can pull that out. I also see that each of my terms has an x in it. So I'm going to factor out a negative x from the numerator. If I factor out a negative x from the numerator, I am left with x squared minus 5x plus 6. In my denominator, I can also factor out a negative, but I have an x cubed and x squared. We have a negative x squared there in common. And if I factor out that negative x squared, I am left with x plus 4. Factoring just a little bit more in the numerator, I'm going to move that negative x over, and this trinomial here does factor. So that trinomial factors to an x minus 2 times an x minus a 3. And I'm just going to bring my denominator over. Now, we did all of that factoring just to be able to simplify just a little bit here. We are going to cancel the negative with the negative, and this x will cancel out with one of those x's, leaving x minus 2 in the numerator, times x minus 3, over an x times x plus 4 in the denominator. Now, at this point, we do want to try plugging in negative 4, but we do need to be careful about how we do that. Now, for our numerator, we can just go ahead and plug in a negative 4. Negative 4 minus a 2 is a negative 6. Negative 4 minus 3 is a negative 7. And negative 6 times negative 7 is a positive 42. That tells me that my numerator is going towards a positive 42. My denominator, you don't want to just plug in a negative 4 because you will get a 0. Keep in mind we are approaching negative 4 from the right-hand side. So if we're taking a look at negative 4 from the right-hand side, we want something directly to the right-hand side. So I would say maybe use like negative 3.9. Plug that in for your denominator and do a negative 3.9 times negative 3.9 plus 4. Now, negative 3.9 plus 4 is a 0.1. All right, so we would be left with this negative 3.9 times 0.1, which is just going to give us a negative 0.39. The point is that it is negative and is extremely small. And the smaller and smaller we make that negative 3.9, negative 3.99, negative 3.999, the closer and closer we get to 4, the smaller and smaller this number is going to be. So our numerator is positive. Our denominator is negative and going to 0. Positive divided by negative is negative. And if it is negative and your denominator is going to 0, which makes your entire function larger and larger and larger, negative and getting larger and larger means that it is approaching a negative infinity. So let's talk about how do we find the following limits, right? So we're going to find the limit as f of x approaches 1, as it approaches negative 1 from the left, and as it approaches negative 1 from the right. They also want us to verify the vertical asymptotes, which we will do using some graphing here. So we want to find these limits. So when it does come to finding the limit of a function, we do want to try plugging in that value that it approaches. So this says x does approach 1, so we would want to try plugging in 1. Now, I typically always start with plugging it in the denominator, and if we plug in 1 in the denominator, we see we'll get 1 squared minus 1. That's really just 1 minus 1, which is 0. So we do see this would get 0 in the denominator, which would make it undefined. So we do know that this function is undefined at 1, right? Because if we plug in a 1, again, we get 1 minus 1, 0. You don't want 0 in the denominator. So that means that this graph should have a hole at 1. Now, since 1 didn't work, we do want to see if we can tweak our example here, simplify it, break it down. Now, this is a polynomial function in our numerator and our denominator, so it is a rational function, but we have polynomials for our numerator and our denominator, which means typically factoring will work here. Our numerator, if we take a look at our numerator, that does factor to x minus 1 times x minus 3. Our denominator is actually the difference of squares formula. That is an x plus 1 times x minus 1, which means we have x minus 1 in our denominator, x minus 1 in our numerator that we can cancel out, leaving us with an x minus 3 in our numerator and an x plus 1 in our denominator. Now, at this point, we can plug in and find the limit of this analytically here. So if we want the limit as x approaches 1. Now, if we go ahead and plug in a 1 at this point, we will be left with a 1 minus a 3, which is a negative 2, a 1 plus 1 in the denominator, which is a positive 2. So it does simplify to a negative 1. So that means the limit as x approaches 1 is a negative 1. When we take a look at the limit as x approaches negative 1 from the left. So again, we want to go ahead and plug in a negative 1 into our function. Negative 1 times negative 1 is a positive 1. And 1 minus 1 is 0. So we get a 0 in our denominator when plugging in a negative 1, which again means that we want to take this, we want to break it down. Now, since we are working with the same function for all three of these, we are using the same f of x, we can go ahead, use the same factoring, and know that this is x minus 3 over x plus 1. Now we're plugging in a negative 1 here. But if we plug in a negative 1 into the denominator, we get negative 1 plus 1, which is 0. So we are going to determine this analytically here. So as x approaches negative 1 from the left, we are going to plug in a negative 1 into the numerator. That gives us a negative 1 minus 3, which is a negative 4. So the numerator approaches a negative 4. In the denominator, we're not just going to plug in a negative 1. We are plugging in a negative 1 from the left-hand side. So we want to plug in like a negative 1.1, right? Something directly to the left of negative 1. If we do that, we are left with a negative 0.1. So our denominator is negative. So if your numerator is negative, your denominator is negative. Negative over negative is positive. And again, if you have a super small denominator like we do here, the smaller your denominator is, the larger your function is. And rules of limits say, based off our sign, if our denominator is small, that makes your function go larger and larger and larger. So since it's positive and growing large, we can say that this limit is going to be a positive infinity. For the third one, very, very similar here. Again, we're using the same function, so we can say x minus 3 over x plus 1. This time we are plugging in negative 1 from the right-hand side. So if we're using negative 1 from the right-hand side, we want to think like negative 0.9. So if we put like negative 0.9 plus 1 in our denominator, we are left with a positive 0.1. If we plug in a negative 1 into our numerator, we do get a negative 4. So look at your signs. Numerator is negative, denominator is positive. Negative over positive is negative. And again, with the small denominator, your function grows large. And rules of limits say that if the function grows large and it is negative, it is going to approach negative infinity. Now, we did find the following limits, but the instructions also say that they want us to find the vertical asymptotes of this function here. Now, if you take this function and plug it into a graphing calculator, plug it into a site online, this is what the graph is going to look like. It's going to tell us that we have a vertical asymptote at negative 1. We have a horizontal asymptote at a positive 1. And the graph is going to look like this, right, so if you plug it into a graphing calculator, it's going to look something like this. But what we know about vertical asymptotes is that if you take your denominator and set it equal to 0 and solve, that should give you your vertical asymptotes. So our denominator is x squared minus 1. But if we set this equal to 0 and start solving, add the 1 on each side. X squared is equal to 1. So take the square root of each side, and x is equal to a plus or minus 1. Based off of the answers that we got here, it does not show that we had a vertical asymptote at a positive 1. It did show that we have a vertical asymptote at a negative 1, and we can see that by this one here. Now, what we should actually know about this graph, very, very similar here. We do have a vertical asymptote at a negative 1. We do have a horizontal asymptote at a positive 1. Our graph is going to shoot off like this on the left. And on the right-hand side, it's going to look very similar. But what we found out here, again, we know that our denominator cannot equal a positive or negative 1. And we see that our graph shoots like this on this side here. But notice at a positive 1, like nothing's going on here. At a positive 1, there should be a hole in our graph. So the correct graph for here at a positive 1, we should have a hole here in our graph so that it's going to connect like this. When you plug it into a graphing calculator, it doesn't show that here at this point here. You have to know that by doing the calculations, setting that denominator equal to 0 and solving. So we know at positive 1, we have a hole here. At negative 1, based off of our graph and everything that we found out, we have the vertical asymptote at x is equal to negative 1. And to end this section, let's talk about limits of trig functions at infinity. So let's find the following limits. Let's find the limit as theta approaches 0 from the positive side of cotangent theta, and then the limit as theta approaches 0 from the negative side of cotangent theta. Now, one of the first things that we are going to want to do here is hopefully remember that cotangent theta is equal to cosine theta over sine theta. So that's the first thing that we're going to want to do here is I'm going to say that the limit as theta approaches 0 from the positive side of cotangent is the same thing as the limit as theta approaches 0 from the positive side of cosine theta over sine theta. Now, if we plug in 0 into this function, cosine at 0 is a 1. It's going to approach a positive 1. Sine at 0 approaches 0. So if you remember the sine function, right, the sine function looks something like this. As it approaches 0, as it approaches 0, it does go to 0. So looking at this analytically, our numerator is a positive 1. Our denominator is positive. It is coming from the positive side, but approaching 0. So the denominator is also positive and approaches 0. Positive divided by positive is positive. And again, rules of limits say that if your denominator approaches 0, that makes your function arbitrarily large. So if it is positive and arbitrarily large, the limit as it approaches 0 is a positive infinity. Now, when we look at this, the limit approaches 0 from the left-hand side. All right, so cotangent, we're going to do the same thing. We're going to break this up to the limit as 0 approaches, the limit as theta approaches 0 from the left-hand side of cosine theta over sine theta. All right, so we're doing 0 from the left. Now, cosine of 0 is still a 1. So our numerator is still going to approach a positive 1. Now, sine theta from the left of 0 here. Again, sine theta from the left, it is negative. Right? It's negative and it's going to approach 0. So we're looking at it from this side here. Negative and approaches 0. So rules, right? It is positive in the numerator, negative in the denominator. positive divided by negative is negative. And again, if your denominator approaches zero, it makes your function arbitrarily large. And by definition, if it is negative and arbitrarily large, it is going to approach negative infinity.